Hello, 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 friends. This is, yep, you guessed it, Mr. Folly. Almost all my pen is writing now. And we are hopping into equilibrium, the most exciting part of chemistry, where we get to see that things bounce back and forth. All these things are in there. They'll make sense to you after we're done with it. But let's go ahead and hop right into it. So, overall arching purpose. So equilibrium means things are going back and forth at the same rate. So do you see how we've got X number of bowling pins going left and going right, okay? So that both happens at the same time and it never really stops. You can't really say that this guy's got 3 or 4 and isn't counting anymore. It doesn't stop. It goes on forever. Think about it. Does water evaporate or condense in the atmosphere? The answer's both. Wow. So what this is getting us to is, oops, let's see if I can move this. What this is getting us to is the fact that some things are going in both directions at once. So, equilibrium expressions. Reactions go both forward and reverse. So I want to hop right to this. So we hear the word equal in equilibrium, right? What's equal in equilibrium? Rates, not amounts. Rates, not amounts. Okay. So reactions go both forward and reverse. So I have hydrogen gas plus oxygen gas makes water. And water can also decompose into hydrogen and oxygen gas. Both those things can happen. They will not necessarily have equal amounts, but they will have equal rates. The rate of people in and out of the room is the same every passing period. Bing, bing, bing. 24 people in, 24 people out. But the amounts of people are very different. We've got 24 glorious people in this room, and me. But on the outside, there's not 24 people. There's 6 billion people, or whatever it is. I'm not very good at counting people. So the amounts are not equal. But when the bell rings, 24 leave, 24 come in. Second hour, ding, 24 leave, 24 come in. Ding, third hour, 24 leave, 24 come in. You get the idea that the rate is the same. And the amounts will be constant, but not equal. Equilibrium constant is K. So the reason why is the Germans used to dominate science around the 1800s or so, and they spelled constant with a K. So a lot of this work was done in Germany, and that was why constant still held that K. My really old geometry and trig teacher told me that if I wanted to do math and science, I should take German because that's the language it's spoken in. The language I think it's spoken in now is English, to be honest with you, but that's okay. K means equilibrium constant. What an equilibrium constant is are products raise their coefficients over reactants raise their coefficients. This is divided by bar. Okay. So note, if something's in brackets, that means it's molarity. So only aqueous solutions and gases are included because they're the only ones that can have varying molarity. You omit, which means leave out, solids and liquids as their concentration is the same. So they don't affect the rate. Equilibrium means equal rate. We don't care about amounts. Okay. So if I have a solid, if I have a bar of gold and I have a ring of gold, I should have made this gold, but I'm colorblind, so I wouldn't know anyway. They would both have the same concentration of gold, which might be 1 gram per milliliter or something like that. It's heavier than that. So 14 grams per milliliter is closer to the density of gold. Okay. A K larger than 1 has more products than reactants. This means products are favored at EQ. So you should get used to EQ being the abbreviation for equilibrium. And use that abbreviation. K less than 1 has more reactants than products. This means reactants are favored at equilibrium. So favored are the words we use, and you know what's favored, reactants or products. So when I look back at hydrogen plus oxygen makes water, write the K expression. K is going to be products. This is omitted. Over reactants, H2 squared, O2 to the first power. So what do I put? Okay, so if I have a solid or a liquid, its molarity or is constant, so we're just going to get folded into this. The K expression can't be 0, so it's got to be just kind of the placeholder of 1. So did you note we use 1 for liquids and solids? But most of the time you just leave it off. But that's it. Oh my goodness gracious, look at this dude. So here I've got K. I'm going to start with my products. Solid, I don't care about you. So there's my product 1. Product 2 is aluminum sulfate. No coefficient, so no exponent, right? Nothing here. Over solid over MnSO4 in brackets. And I use this one because it's aqueous, so its charge can change. I'm sorry, its concentration can change, not its charge. All right. Q is the reaction quotient and is similar to K. Notice it's the same thing. Products over reactants raise their coefficients. This looks exactly like K. It is the same formula, but at a certain point in time, it is probably not at equilibrium. Okay? So if I ask, what did you do on your birthday? That's different than what do you do on Tuesdays, right? So your birthday is special. Equilibrium is special. So don't forget, if it says K, it's got to be at equilibrium. That's special, right? So to simplify, Q can be products over reactants in our head, right? So if Q is greater than K, so I'm gonna write this right here. So I've got products over reactants. I'm gonna kind of leave out the coefficients, just kind of thinking about it in simplistic form. If Q is too big, right? Products over reactants. So if I have too many products, so I'm gonna start getting rid of products. Remember, I have reactants, yield products. So if I have too many too many products, I'm going to start shifting back to the reactants, left-hand side. I abbreviate left-hand side LHS quite a lot, like LTHS goes out there to reach K. If Q is too small, again, I have products over reactants. It would be too small because I'd have too many reactants, right? So if I have too many reactants, they start forming products, and that will shift to the right-hand side. So when reactants turn into products, that's shifting right. All right, so let's take a look. The reaction above has K equal 2.55 E negative 3. Write the K expression. Easy peasy. K equals, see ya. Oh my goodness, look at this. P2O5 to the 6th times SO2 to the 9th over P4S3 to the cubed. All right, write the Q expression. That also equals Q. Good. So then they give us, if Q is this, and then is the reaction at equilibrium. So what I'm going to do is I'm going to solve for this. So I'm going to do Q, this is Q, equals P2O5, 0.05 to the 6th. SO2 is 0.95 to the, my goodness, 9th over P4S3, 0.11 to the 3rd. Thank you for calculators, God. 0.05 to the 6th times 0.95 to the 9th divided by, oh, bad calculator, 0.05 to the 6th, enter, times 0.95 to the 9th, enter, divided by 0.11 to the 3rd. I'm used to an older calculator that wouldn't keep everything in the exponent for me. So my Q is 7.40 E negative 6, and I need to compare that to 2.55 E negative 3, and I got that from here. This is K. So notice Q is less than K. So is it at equilibrium? No. Which way will it shift? Well, if Q is less than K, so what happens here is I have too many reactants. So it will shift to the right-hand side. Okay, so K is just kind of like this ratio that makes things good, like pi, right? So 3.14159, what is it? It's the ratio of, oh, I don't know, what is it? Like circumference to diameter or something or other like that. So this is what we're doing, is we're just trying to figure out what happens to get this to pi. Only our pi will be different for each one. A system has a Q of 2 and a K of 2.00 E negative 3. I'm going to rewrite this. So 2.00 E negative 3, because I know people have been struggling with scientific notation in class. 1, 2, 3, decimal point, 00. So I have 0.002 compared to, that was K, compared to 2, and that's Q. Do you see how Q is bigger than K? Is that at equilibrium? No. Which way will it shift? Q is too big, so products over reactants. So it's going to shift to the reactants, left-hand side. That's it. Toodles.